Good day, everyone. Welcome to our Math 111 class. This is Calculus 1. So today we are going to review our knowledge or our skills on function. So we have different types of functions that we're going to discuss today. Since this topic is a very long topic, so I'm going to divide this video presentation in several parts. So before we go into details, let us have first the objective of this lecture today. So at the end of the period, you should be able to define and explain the concept of relations and functions, describe and discuss the difference between relations and functions, sketch and interpret the graphs of relations and functions, determine and describe the domain and range of relations and functions. So when you speak of relation, it is a set of ordered pairs. A relation is a set of ordered pairs. So the set of all first elements, we call it abscissa, in the ordered pairs is called the domain of the relation. The set of all second elements, we call it ordinate, is called the range of the relation. For example, if you are given here set A that contains ordered pair of elements 1, 3, 2, 4, 3, 5, 4, 6, 5, 7, and another set here that contains an ordered pair of elements negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 4. So the domain and range is given by the following. We have DOA, it means domain of set A. It contains elements 1, 2, 3, 4, 5. So these are the first element of the pair, of each pair of this ordered pair elements here. So 1, okay, that is the first element of the first pair. Then 2, the first element of the second pair. Then we have 3, the first element of the third pair. And 4 is the first element of the fourth pair. And 5, the first element of the fifth pair. Alright, now for the range, range of A contains element 3, 4, 5, 6, 7. So these are the second element of each pair. So we have 3 here as the second element of the first pair, ordered pair. And then we have 4, the second element of the second pair. And 5 is the second element of the third ordered pair. And 6 is the second element of the fourth ordered pair. And 7 is the second element of the fifth ordered pair. Okay, and for the set B, so we have here DOB, or the domain of set B. It contains elements such as negative 2, negative 1, 0, 1, 2, 3. So again, these are the first element of each ordered pair in the set. So we have minus 2, okay, this is the first element of the first ordered pair. Then negative 1, the first element of the second ordered pair. Then 0, the first element of the third ordered pair. And 1, the first element of the fourth pair, ordered pair. and then we have 2, the first element of the fifth ordered pair, and 3, the sixth, or sorry, the first element of the sixth ordered pair. Right? Now for the range of B, it contains elements 0, 1, 2, sorry, 0, 1, 4, 9. If you examine set B, so there are 1, 2, 3, 4, 5, 6. So there are 6 ordered pair. Now, if you look at the elements here, there are only 4. So what do you think is the reason behind? And take note, this is arranged in ascending order from lowest to highest. So there are only 4. The reason is that if you examine the elements here, we have on the for the second ordered pair, we have negative 1 and 1. Okay, we have the fourth ordered pair 1 and 1. So for the second element of each pair, we have two the same number 1 and 1. So we need to write them, or we need to write once only this number. So that's why we have a 1. And of course we started with 0, the lowest. And then next we have 4. We have 4 here in our first ordered pair, second element, and we also have the second element here at the fifth ordered pair. So same number, so we need to write only 1. And then finally we have 9. Alright, so these are the domain and range of the given function expressed in terms of a set. Now to emphasize this part clearly, so I colored the first elements by blue and the second elements by red, no, to distinguish these numbers, the range, the domain, and the range. So if you look at here, domain of A, so we have 1, 2, 3, 4, 5. So this is exactly the first element of each ordered pair, right? And we have here for range of A, 3, 4, 5, 6, 7. So exactly the second element of its ordered pair, 3, 4, 5, 6, 7. Now for B, so domain of B, we have -2, okay, we have -1, we have 0, 2, and we have 3. Right, so these are for the domains. Now for the range, we have 3, 4, 5. 3, 4, 5. Here we have for B 0, 1, 4, 9. So again, we arrange it in ascending order, starting from 0 up to the highest number, which is 9. Alright, I hope it's clear with you. Okay, so these are the domains, and these are the range. So the ordered pairs that comprise a relation are frequently given in some way other than set notation. For example, this set notation, we have set A contains ordered pair of elements 1, 3, 2, 4, 3, 5, 4, 6, and 5, 7. Then the given relation may be presented in tabular form, something like this. We have x, we have y. So all the value here for x, that is for the abscissa, and these are the value for y. These are the ordinate. The ordered pairs that comprise a relation are frequently given in some way other than set notation. So another way of presenting this relation is through by correspondence diagram. Okay, so we have segregated the first elements into this part here, and second elements on this part or side. So we have 1 3, 1 corresponds to 3, so 1 corresponds to 3, we have 2 corresponds to 4, 3 corresponds to 5, 4 corresponds to 6, and 7 corresponds to 5 corresponds to 7. Okay, so there is a 1-to-1 correspondence. 1-to-1 correspondence from the first elements to the second elements. So a relation can also be written as a formula. So if you're given a relation expressed in set notation, so this can also be expressed in a formula or written in a formula. So we have A is a set that contains X and Y, or set A contains ordered pairs of X and Y such that X is an element in this set 1, 2, 3, 4, 5, and Y is equal to X plus 2. Okay, so that's how we write the set notation of relation into a formula. Another way of presenting is through a graph or by a graph. So we can present a relation expressed originally as a set notation by a graph. Okay, so it's like this. So we have these points that corresponds to each of these ordered pair. Alright, so if you look at this, this is okay. So we'll label this one to make it clear. So assuming this is 1 unit here, then this is 2, and this is 3, and then this is 4, and we have 5, and we have 6, and so on. On the other side we have 1, 2, and 3, and 4, 5, 6, and 7. Alright, so this point corresponds to 1 and 3. So it means that 1 here is the distance from this point to that point, and 3 is the distance from this one, which is 1, that is the distance from the origin towards this. Okay, and this is 1, and this is 3, so 3, 1. So 3 for the ordinate, 1 for the abscissa. So 1, 3. X, this is in the form of x, y. So unahin natin yung x, which is 1, y is 3. Then 2, 4. So 2, 4. Okay. 2, 4. So it means that from the origin towards this, that is 2, and going up, so we have 4. So 2, 4. Okay. Then so 3, 5. So 3. Alright, so extend from the x-axis towards this point. Then this is 5. So 3, 5. Then we have 4, 6. 4 is the distance from the origin towards 4. Okay, and then we have 6, so it means 6 vertically. So we move 6 vertically. 1, 2, 3, 4, 5, 6. And then finally we have 5, 7. So 5, 7. Okay, so a relation can be illustrated by a graph. So this is a graph. We just connect all these points and we will form a straight line. A function is a special type of relation such that each element in the domain corresponds to exactly one element in the range. So each element in the domain, meaning the x values, corresponds to exactly one element in the range. So if we have that condition satisfied, then we can consider the relation as a function. So for every value of x, there is one and only one value for y. For every value of x, there is only one and only one value for y. Okay, is that clear? Alright, so let's continue. So for every value of x, there is one and only one value for y. So there is one and only one value for y. A function is a relation in which no two ordered pairs have the same first element and distinct second element. So a function is a relation in which no two ordered pairs have the same first element and distinct second element. For example, you are given here different set notation of the function or functions. So for set A and B, so they are all considered functions. So why? Because we have a one-to-one correspondence here. 1 corresponds to 2, 2 corresponds to 4, 4 and then 3 corresponds to 6, 4 corresponds to 8, 5 corresponds to 10. Here for B, set B, so we have negative 2 corresponds to 2, negative 1 corresponds to 1, 0 corresponds to 0, 1 corresponds to positive 1, 2 corresponds to 2, and 3 corresponds to 3. So these two are functions. While C and D, so if you examine them individually, we have 0 corresponds to 0, 1 corresponds to 1, and we have 1 corresponds to negative 1, 4 corresponds to 2, 4 corresponds to negative 2. So this ordered pair, we have 1 as the first element, and 1 is a second element, but the next ordered pair, we have 1, negative 1. Okay, so and so do with this 4 corresponds to 2, 4 corresponds to negative 2. So these are pair the pairs that makes this function not a function, or relation not a function. And for this one, for D, we have 0, 5, 1, 6, 1, negative 6, 2, 7, 2, negative 7. So 1 corresponds to 6, and 1 corresponds to negative 6. So they have the same source, no? The same abscissa, and also with this. So it cannot be. So that's why this is not considered a function. and so with this one. In terms of equation, a relation is not a function if y is raised to an even exponent, or if y is inside the absolute value bars. Now, for example, if we are given this, so this is the set notation of a function. Set A is set A or contains an ordered pair of elements x and y such that y equal to x plus 6. So this is the first function in set notation. And B is B set B contains elements ordered pair elements such that y cube equals absolute value of x plus 5. And C contains an ordered pair of elements x and y such that x squared plus y equals 10. So they are all functions because the condition above are satisfied. So if you look at the exponent of y here, this is add, understood to be 1. This is add also, and this is add also. So we can proceed with the next. While D contains ordered pair elements x and y such that x plus y squared equals 7. So if you look at this part here, we have y was the exponent of 2, and for E contains ordered pair of elements x and y such that x plus absolute value of y equals 3. So they are not functions. Why? Because the exponents here is 2, and here y is inside the absolute value function. So these are considered not function. These relations are not considered functions. In terms of graphs, the graphs of a function can be intersected by a vertical line in at most one point. For example, if we are given these two graphs here, to determine whether each of them is a function, then we need to test using the test, vertical line test. So we just draw a vertical line, okay, hitting at one point every time you draw a line vertically and touch with that line. And so do with this parabola facing upward. Same restriction. So you just need to see if your vertical line will touch only at one point. So no two points that should be intersected by the vertical line. So in that case, it's a function if that condition is being satisfied. Okay, so what I was saying, a while ago, so we just draw a vertical line. Okay, so this is the point of intersection. So you see our vertical line touches only at one point. So this is normally what we're doing. Or if you draw this line, so of course this line is intersecting at this point, right? At this point. And so do with this vertical line, also intersecting at this point. Or this one also here, if you draw a vertical line, something like this, it will intersect here. Or if you draw a line something like this, it will intersect also. So therefore, you can say that parabola openings up is a function. But a parabola that opens to the right or to the left, or even a circle, is not a function, since a vertical line test will intersect these graphs at 2 points. Now, for example, you have here parabola opening to the right or parabola opening to the left. So when you draw a vertical line, so it's clearly very helpful. Okay, so if you draw this vertical line, so you will notice that the line intersect at 2 points of the curve or the function. Or if you draw it here, so this is also the intersection. So in this case, guys, we can say that this is not a function. Okay. Next, to determine if an expression is a function, derive the expression for y and analyze if any value of x will have exactly one value of y. Okay, so we need to determine that after deriving the expression for y in terms of x, so we can see that there's only one value, exactly one value of y for any value of x. So for example, if you're given 1 plus x, so example number 1, we have x plus y squared equals 4. Okay, so express y in terms of x, so you can transpose this to the other side. Okay, so we have therefore y, so I'll just put it here. So we have y squared equals, so in transform we have 4. Okay, this 4 here, and then this one that is being transpose. Okay, so this becomes minus x. And you solve for y, you have to take square root on both sides. So on the left side we have only y equals, on the right side we have two values, plus, this plus and minus square root of 4 minus x. Okay, so this is now the value for y. So y has two values, so therefore this is not a function. Now second example, we have y plus x squared equals 5. So we just transpose x squared to the other side, retaining y on the left side. So we have therefore y equals, so on the right side we have originally 5. Okay, so we have 5, then minus, so this one transpose, so minus x squared. Okay, so since the exponent of y is understood to be 1 and odd, and therefore we have y plus x squared equal to 5 as a function. Then the third one, we have x y squared equals 1, or x times y squared equals 1. So to solve for y here, so we need to first divide both sides by x. So when you divide the left side by x, so what is left will be y squared equals 1 over x. So again, our y has a power equal to 2. So to solve for y, we take square root on both sides, so therefore we have y equals square root of square root of 1 over x. And take note, we have two values for y. So this is plus and minus. Okay, so for every value of x, you have two values for y. So that makes this expression not a function. Alright, so two of them are not functions. Then for functional notation, we have if f is the function having as its domain the variable x and its range the variable y, the symbol f of x read as f of x or f at x denotes the particular value of y that corresponds to the value of x. For example, if f contains an ordered pair of elements x and y such that y equal to 2x plus 3, then we can write the function in the form of f of x equals 2x plus 3. Alright, so we replace this a little complicated expression by using this. They're just equivalent. Okay, so we can rewrite this complicated notation or function into this kind, simpler to deal with. Another example, if g is of x and y, it means g is a function that contains ordered pair of elements such that elements y, x and y such that y equals the square root of x minus 5. So this can also be written as j sub x equal to the square root of x minus 5. Now we have here a condition that if a function does not model data or verbal conditions, its domain is the largest set of real numbers, so for which the value of f of x is a real number. So we need to exclude from a function's domain real numbers, the number or numbers that can cause division by 0. And also we have to exclude from a function's domain real numbers that result in a square root of a negative number. Alright, so we have to remember this concept so that we can use it in the next few slides. So this is finding a function's domain. For example, find the function's domain for this function f of x equal to 1 over x minus 5. So to find the domain, so this is fractional. Since this is fractional, we need to equate the denominator to 0. So we have x minus 5 equals 0. Okay, so from here we can solve x. So add 5 both sides. So therefore, or transpose 5 to the other side. So therefore, we have x is equal to 5. So it means that the denominator x, or denominator that contains x, should not be equal to 5. Otherwise, we have 5 minus 5, which is 0. So that can make the function undefined. Okay, so how will you write the domain? Or because before going to that, so we have here because division by 0 is undefined and that not a real number, the denominator x minus 5 cannot be 0. Okay, so to determine that number, so we have x minus 5 equal to 0. So it should not be equal to 0. So we have, so x minus 5 cannot be 0, then x cannot be equal to 5. And 5 is not in the domain of the function. So if you draw the, okay, so we're writing the domain, so we can say that domain, all real numbers are except 5. So any values for r except 5, or any values for x except 5. So the domain, therefore, is written in this notation. So how do we get this one? We have negative infinity, 5, and we have the symbol u here, and 5 positive infinity. So that is determined by this graph. So assuming this is our number line system. Okay, so it approaches to infinity, positive infinity, and on the other side we have the negative infinity. Okay, so assuming this is our 0, 0 or 0 here. So where is 5? So x equal to 5. So you just count 5 units from the origin, or from this point. So we assume this to be 0. So this is 1. We have this 2. And we have 3. And we have 4. And we have 5. Okay, so we have this interval here. 5 is excluded. So we have here and this interval, and the other interval is this one. Okay, so we know that going to the left it approaches negative infinity, going to the right it approaches positive infinity. So what is this here? This is negative infinity for this interval, negative infinity for the left side, and we have here 5. So 5, so positive 5. Okay, so that is for this interval. And for the other interval, this interval here, so we have 5. Okay, so we have to use parentheses also. And this is positive infinity. Okay, so this is, and then we have union, the symbol union. It means that we have to combine them, the values that belong to this part here, this interval, and also on this interval here, excluding 5. So because 5 will make the function undefined, so we exclude that number. Okay, so another example here in finding a function's domain. So let's consider the function g of x equal to square root of x minus 7. So we have a radical here. So the condition here is that the radicand should not be a negative number. So let us find now what number that can make the radicand a negative. If that becomes 0, there's no problem. So for as long as it's not negative. So to how to determine, we have to uh, equate or express this or solve the value for x here. So x minus 7, x minus 7, so x should not be, what do you think? So if x is equal to 7, that becomes 0, so we can still get the square root of 0, which is 0. So when that will becomes negative, the radicand x minus 7, so this should be less than, this should be less than or equal to 7. So this expression here should be less than or equal to 7. So, oh sorry, we need to make it 0. So x minus 7 less than or equal to 0. So therefore, solving for x, we have x, transpose this to other side. So less than or equal to what? So you transpose this minus 7 to other side. So x is less than or equal to 7. Okay. So therefore, the domain, so we're doing this because we know the condition is that the expression under the square root must not be a negative, or it should be non-negative. Okay, so therefore the domain will be, then x must be greater than or equal to 7. Sorry, this is not this is wrong. Okay, so we have to follow this one here. So we have to find out the value of this radicand by using this x minus 7 greater than or equal to 0. Okay, so I hope you understand this. So then x must be greater than or equal to 7. Otherwise, this make the function undefined. So the domain therefore is x, like 7, or the interval is from 7 to a value that reaches positive or approaches a positive infinity. Okay, so it means that if this is our 0 here, and this is our 7, assuming ito yung 7 natin, and this is our positive infinity, this is our negative infinity. So x must be greater than or equal to 0. So x right?